about the file system for flash storage and mobile. So I'm happy to give you the presentation about the file system. This file system was just released a month ago in a Kernel mailing list. And this was a very hot topic in the last month in the Kernel mailing list. So we got many feedback and comments. Thanks for all the comments. So we could have patch it for the improvement. So we try to we still try to make it mainline, and we are working on that very actively. So this is a presentation about the design, why we have to design a new file system for flash storages and how we develop. So that's the theme of the session. So let me introduce myself. I am working in a Samsung memory business unit. So yeah, that's why I focus on the file system issue for flash storages. So this topic can be very specific for mobile embedded, but also have some relation to the SSD device. Okay, this is sort of agenda for the talk. So I will briefly talk about the flash storage characteristics, and also talk about design points of the file system, and I will give you some performance evaluation results, and I will conclude. Okay, so as you know very well, so NAND flash is very widely used in many kinds of mobile devices, from computer, smartphone, and these are mostly have a lower price because we have many. The manufacturer have improved the manufacturing process from single level cell to the multi-level cells. So even we have reached to the 3-level cells now. So Samsung has just announced the TLC SSD for the client PC. So we are expecting very quick rise of SSD in the market, especially in the next couple of years. So this is very hot trend in the storage devices. So we are moving from the LCD hard disk drive to the SSD. And actually in mobile devices, most of storages are flash bases. So previously we have used raw NAND flash, but we are moving to the some more high-end, high functionality devices like eMMC. So that has that provides a higher density and a small form factor. So the eMMC has typically have 64 gigabytes. So that's very promising for the storage devices in a smartphone. So mainly this file system is about the mobile storage, mobile flash storages. So we will focus on that here. So this is just a little bit about the file system, what the file system is doing in the system. So as you know well, it manages the memory, and also the file system is maintaining the storage spaces. So it has a directory or file structure and index structure. So all of these are very important components in designing a new file system. So I will talk briefly about each component. Maybe I cannot cover all of that component, but I will try to give you an overview of that. So this is a flash issues in the storage. So NAND flash is very different from the hard disk drives. Hard disk can be written without erase, but the flash memory is different. That has to be erased before writing. And this causes many problems in software design, but we have we have a couple of file systems for the NAND flash memory, like the JFS2 or ELCE. So after that, we came to a flash translation layer, which is the piece of software running in the embedded controller, which is inside in the storage device itself. So that software is controlling the garbage collection and wear leveling and bed rust management. So all of those functionality is run by the storage itself. But there is an issue in FTL devices. So because the FTL is running on the embedded controller, that controller is very different characteristic in computing power and the memory resources it can use. So even in the eMMC or SD card, we have many restrictions on using the more memory resource inside the card devices. We have only very small memory footprint to use for the FTL running. So we end up with a poor random write performance, and also it causes a lifetime limitation. So these two problems are major issues in FTL device design. So what about the file system for FTL devices? I think there was some discussions in a mailing list about how to change the existing file systems to be aware of the FTL device's characteristics. I think that is still going on, work. And our file system is addressing the file system issue from the ground up. So we consider the flash FTL characteristics, and we design to reflect that kind of characteristic in our file system design. So the major goal is to actually the device has a piece of software actually, and also we have the host file system stack. So these two layers are running without any information previously. So actually those two layers should be coordinated in some sense, but exchanging the information to coordinate is very difficult because it requires a standardization of the interface. So we try to coordinate the FTL behavior by changing the file system access pattern to the device. So that's a major motivation of our file system design. So as I said before, the random write issues are a major issue in flash FTL device. So we tried to make mostly sequential write pattern in a file system, which is very preferred by the FTL device. So we follow the approach of the low structured file system. That's a very classic idea borrowed from the following paper. So most of the inode and metadata structures are borrowed from that, but we have designed a little differently to consider the flash characteristics. And this is a high-level picture of how the low structured file system was constructed in the previously. So it has the superblock in the left top. Superblock and checkpoint has that fixed location, so we should write them in a fixed location. And another thing are all the load. So it is appended to the clean load when there is any file system changes. So inode and file data and directory, and also some kind of inode map, which is referencing the latest version of the inodes, are all loaded in a sequential pattern. So that's very useful for hard disk write performance. And we decided to use this kind of concept because that sequential write is also good for the FTL devices. But the problem is the conventional LFS design has a one-link problem. I will talk about that later in more detail. And also it has a high cleaning cost. So we don't have any problem if there is a clean space to load that data. But if we are running out of the clean spaces, the problem happens because we have to do cleaning in the file system later. So it should read some kind of valid blocks from the disk and write to the other places. And also we have to update the metadata as according to the data changes. So that's all about the cleaning cost in the local storage file system. So two issues are the major issue when we have to design it, redesign it for tier device. So most of the next coming slides are handling about the cleaning cost and one-link problems. Yeah, this is an overview of file system design point. Number one is alignment with FTL operation unit. As you know, the FTL is operated like operated using a super page or a super block. So that's the kind of flash device operation units I will talk about later. And we have avoided the metadata update propagation by using Indirection Layer. And also, we address the cleaning cost with the multi-head loading scheme is already introduced in the conventional LFS, but we use that concept by aligning with the FTL multi-load characteristics. So that's the key point in our design. And number 4 is adaptive write policy for high utilization. So even though we can do cleaning very efficiently in normal case, but chances are we came to a very high utilization situation. So at that case, there are many difficulty in moving data blocks, and that's mainly because of the one-to-one problem. So we tried to address it by changing the write policy at the situation, so we could get graceful performance degradation at that such kind of stress situations. So I will briefly talk about some FTL device characteristics. So firstly, FTL function, the key functions are address mapping and data collection. So regarding the address mapping, we have 3 options. First one is a block mapping. That's very naive method. So in every case, in every write operation, the flash block is written again with only a small change inside that. So the page, only a page is updated, but all the block pages are retrieved from the storage and written back again after erasing. So that causes a very performance bottleneck. So I think the block mapping is not well used in most of storage devices now. And second one is page mapping. The page mapping requires a very memory resource to cache all the mapping tables. So the mapping table has all the page-based translation information. So for a bunch of FTL mapping entry should require a much memory inside the storage itself. So this cannot be an option in designing an eMMC card, even as an SD card, because it has many cost restrictions and form factor restriction, and also power limitations. So the most promising option is the hybrid mapping, because it has tried to achieve the the small memory footprint and also the high performance of the page mapping. Even it cannot achieve the level of the page mapping, it can get some near performance of the page mapping. So inside the eMMC architecture, we have a memory interface for the NAND interface, and also we have the eMMC interface logic, and the controller is running the FTL functions inside. So this is very restricted condition of designing the hardware and also software. And I will talk about more detail of the hybrid mapping, because our design is mostly about how to optimize the hybrid mapping FTL, optimized for the entire storage workload. So we have three options for hybrid mapping. First one is EAST. That's an acronym for Global Associative Translation. And also the FAST is fully associated. So here, the associativity means that how many data blocks are associated in the log block. In the upper side, you can see the two log block here and four data blocks in the on the DAC. So I'm showing here. This is about the cell-associated scheme. Cell-associated scheme using a number n is the data block group size, and the number k means the log block count for each data block group. So if we have more k, then the performance can be increased. But we cannot increase more, because it requires a more NAND flash or provisioning in the storages. So mostly we have to use a small number of log block for data block group. But there is a problem in merging cost, because it is the worst case we have to full merge that the log block and data block should be merged together to form a new block. So here, in the full merge case, we have to copy all the valid blocks from the log block and data block into a new clean block. In other case, a partial merge means we copy only a part of the block. So, for example, if the block is consisting of 100 pages, then we can copy only a part of the block's pages. And the switch merge is the best case. This can be achieved by sequential write pattern. So if we write from the first page of the block to the end of the block, then it is very simple to merge that block, because we just use the log block as a new data block. So we don't have to copy the value page, but we change the mapping entry. So our goal is to make the FTL algorithm to behave as a switch merge pattern as mostly as possible. So we try how to drive FTL to the switch merge. That's the key point. And FTL has a super block and super page geometry unit. So super block is a unit size for the simultaneously readable size. And super page is the simultaneously programmable unit. So because we have many NAND flash chips inside the eMMC, the embedded controller has many channels for the parallelism of those NAND flash chips. So we have The controller programs multiple NAND flash pages together, so that enhance the bandwidth. So how can we design our file system in terms of the segment size? That's the first question we have. So if we have if we have a bigger segment, then we can achieve a sequential write performance. So as the graph shows, as we increase until the 8 megabyte record size, we can achieve the most peak performance of the storage. But we have the problem of a cleaning cost, because if we have a large segment, we have a very large cleaning cost in the file system again. So that's the trade-off relations. And also, the FTL has many very interesting feature, because it has a multiple log block. I said before, the hybrid mapping has a log block for each data block group. There are many log blocks for concurrent page programming. So, but we have to know how many streams, sequential streams, can be offered for the offered by the underlying device, and we have to also identify the data block group geometry. So that's the second question, and this has implication for multi-head logging design in our case. So in the graph shows that as we increase the number of processes, these processes are running the sequential write. Each of them are writing in a file by direct I/O in a different position, starting from a different position. So we simulated a concurrent sequential write streams together, and the overall throughput is shown here. So as you can see, the number of processes can be increased until 6 without a small performance degradation compared to the number of process 1. But after that, the performances are much degraded. So this is a very interesting characteristic of the FTL device. So our file system is aware of the FTL characteristic in some point. So firstly, all of our file system data, the low structured metadata, is located in the forefront side of the volume, so that we can exploit some caching features inside the devices. So if we mostly the metadata area has many 4K small random write access pattern, and device can have acceleration feature to cover such kind of small random write, which are focused on a small logical block ranges. So that's our first design point. And second, we have aligned the main data area to the zone size. The zone size means data block group, as I mentioned. And also the cleaning operation is done in a unit of section. The section is matched to the FTL unit size. So the question is how to do the garbage collection in the both layer in file system and FTL. In both layers, they are running their own GC algorithm, but we have to do a switch merge in an FTL side. That's considered the best case for the performance. So we tried to align the file system cleaning size and the FTL cleaning size together. And here, in in the main area, data is loaded in a multi-head logging fashion. So we have a six head here. This is an example, and we have more options. For example, 2 head or 4 head. So in those cases, each segment has their own data type, which they can accept. So we separate our data set based on the update frequency. So hot data means they are very frequently updated again. So they are merged together in a hot data segment, and also cold data, which are not updated very well, that are merged together. So that helps. We can reduce the cleaning cost in the file system and also in the FTLA. So this is about how we address the wandering tree problem. So conventionally, when we update the file data block, then we have to update the direct node and indirect node and file inode and even the inode map and checkpoint block. So all of these dependency cause the problem. So we decided to introduce the indirection layer for the node concept. So node means the metadata blocks for the file. So here, the dashed line means the cross-reference by looking up the indirection layer table where we show the NAT over there. So node address translation layer, translation table has all translation mapping for which node is mapped to which logical block in the file system. So if we change the file data here, so we have to write a new data block. So the new block's location should be recorded in a direct node. So we write a new direct node here. So that's it. And we don't update the indirect node and file node and also the checkpoint node. But we have to update the NAT because we have to update the direct node location in the NAT table. So that's all we have to do. So that reduces the update propagation in some sense. And this is a file indexing structure. We are using the pointer-based indexing scheme. So in our current design, we have support for about 3.94 terabyte for if you're using a 4K byte block sizes. Yeah. And I will talk about some cleaning efficiency aspect. So the cleaning process means we have to select a victim to clean. So we have to read all the valid blocks in the victim segment and move that to the another free segment and use the victim as a clean segment again. So we have to move the valid data anyway. But the goal is to hide the cleaning latency and also reduce the valid data to be moved. And even we have to move the data very quickly. So the major issues are the two things. One is the hot and cold data separation, and the other is victim selection. I will talk about more about the hot-cold separation. So I think this is the heart of the file system design in our case, because the conventional LFS design has some problem in the hot-cold data separation because the hard disk drive has very mechanical arms and in FTL case, as I said, we can have up to typically 6 multi-load without performance degradation very much. So we can have a choice at data writing time. So we classify the data types in 6 categories. So we differentiate from data from node, because the node has very different access characteristics from data. And for each category, we have 3 levels of the update frequency. So this is a current design, and it is interesting to see this kind of extension check for identifying the code blocks. So all of these tests are very efficient because we don't have any need to track the page access pattern. We can know the kind of object type by in the context of the file system. So, and even the extension list can be given by the user in a mount time, or the kind of list information should be provided for the file system. So that's a very static approach to the data separation. And we have also the dynamic separation scheme at cleaning time. So we have automatic background cleaning procedure that's kicked in when the I/O is idle, so it doesn't hamper the foreground I/O performance. And so during the background cleaning, we try to separate the hot and cold data as much as possible. So we have to use a different cleaning algorithm for foreground and background cleaning. So here, the CostBenefit algorithm is designed for background cleaning to make the hot-cold separation efficient. And this is about how to avoid an excessive performance degradation when we have a very shortage of clean segment. And this is it. We changed the write policy from the normal policy is logging after cleaning a segment. But in case there is not enough clean segment, we change the policy to thread logging. So thread logging is writing to the invalidated blocks of a dirty segment. There can be many obsolete blocks in a dirty segment. We find a good segment for the thread logging, and we fill that gaps by the logging. So maybe that causes a random write because the invalidated blocks inside the dirty segment can be very separated geometrically. But we have some chance in optimization inside the FTL because the random write range is very small range. So the FTL can have some choice for optimizing the small range random write. Yeah, this is a little bit about the directory design. This is a kind of independence from the flash characteristic, but we try to optimize the performance because we designed this and developed file system for keeping in mind that we have to use this file system for most of the workload, and for example, the directory operation intensive workloads as well. So we have a multi-core hash table architecture. For each level, we have a hash bucket, and we can compute the hash value for a file name. Then from the top level 0, we try to find a corresponding hash bucket and compare the values if they are matching there. So we can do it very efficiently by because these trees are less overhead compared to the sequential DFC. Yeah, I'm going to talk about the performance. We have measured the recent eMMC from Samsung. That was measured in the Panda with the ARM Cortex-A9. So here you can see that IO zone, sequential read, write, and random read performance are very equal to the ext4 case. But in the random write case, we have achieved a nearly sequential write performance in random write case. This is, yeah, we can expect from because we have LFS design. So mostly we translated the random write to the sequential write for the FTL device. And FSMark and Moni++ benchmark is showing how well the directory performance is going on in FTLS. So especially in a large directory case, as we increase the directory size, we can achieve a more performance gain over ext4. So that's due to our design in a directory hash table. And also in the Moni++, we have achieved a better or even competitive performance in the ext. Yeah.
Is it running in the direct mode?
I'm sorry.
Is it running in direct mode?
Is that running in direct IO mode?
Direct IO mode in which IO zone case?
IO zone.
Yeah.
No, that's running in a buffer service buffer mode.
Do you have results with direct mode?
Direct mode? Yeah, we have, but there's nothing really here.
Is it also represents?
Yeah, the same behavior because mostly we are have competitive performance in the ext4 and superior in case of random write. So similar, and also in direct IO. Actually, when we are doing the IO zone test, we tried to remove the buffering effect because that can be very irrelevantly higher than we can get from the storage performance. But yeah, we have tested for the buffering condition as well. So yeah, buffering performance is also compared to the ext4 case. Yeah. And this is performance on the Galaxy Nexus. Actually, we have some demonstration booths in the floor, and we ported that file system on the Galaxy Nexus to see how the user can achieve the performance gain when we have a context sync or app installation. So we can have some 20% in a context sync. And we did also experiment for the aging condition because, as you know, the global structured design can get the performance drop in an aging condition. So we tried to do that by using the daily user access pattern. So we do some context syncing for a couple of times to age that device, and we measure that after aging. So even though there are still some drop in performance, we can get a better performance than the ext4 case. So it's very strange that because in app installation time is better in aging condition. So we don't know why. So, and that's it. And also, I want to also note that the multitasking performance is very well because as you can see, IO zone with the app installation case, we are running two different tasks. So here the FFS can get higher performance even in multitasking cases. And this is showing the victim selection policy effect. So cost-benefit policy is trying to separate the hardcore data because without that kind of a hardcore separation, as you can see, the greedy policy is selecting a victim segment just considering how many validated blocks in a depth-30 segment. So that choose a segment with a lower number of validated blocks because it gives a lower cleaning cost for that cleaning. But that doesn't, that cannot separate the hardcore data because they don't consider any of the frequency of the data itself. So after test iteration goes on, the cost-benefit case, the moved blocks are decreased because the code data are merged together. So the code blocks are not involved in the code cleaning operation. So that's why we can achieve a higher performance with the cost-benefit in a sustained case. And this is about the adaptive write policy case. So this is very stressed condition. We try to evaluate if we have designed the adaptive write policy very right. So before the adaptive write policy, we try to clean the segment in any way. In that case, as you see from the purple line, purple line means 97% utilization. That's very high utilization. So we don't have much free spaces there. So it's very stress condition. Here, without adaptive write policy, the performance is very degraded in the sustained state. ext4 case is about 4 megabytes in even cases. So after using the adaptive policy, we could achieve the competitive performance of the ext4 case. But the important point is in less utilized condition, we could achieve a better performance than ext4 because we guess that the FTL side there are some chances of partial merge cases compared to the ext4 because mostly we guess that the FTL running with the ext4 has a full merge inside, but hopefully, presumably this performance gain is from the we had more chances of partial merge cases. So this is this talk was about how we designed the file system and what kind of performance data we could get from the Android phones. So mostly this file system is written for the mobile storages like the eMMC and SD card. But we can expect some benefit of the sequential write case for SSD case as well. So currently we are very actively reviewing the code in LKML, and we have just released the version 3 patch, and we hopefully can get into the next version. Yeah, that's it. So, any questions?
You were mentioning about you were mentioning about the one block called NAND. What is that? Can you repeat it? What is that? NAND. Yeah, there was one block.
Block size?
Yeah.
Block size?
No, NAND module.
NAT module.
Yeah, NAT module.
Okay. What is the size of the NAT?
No, what is actually that does?
The function of NAT? Yeah, that's here. So NAT is not shown in this diagram, but without NAT, we have to update all the node blocks according to the node blocks should contain the logical block address of each file data block. But in our case, each node block has a virtual logical block, which is a unique number for that node. So yeah. So the node ID means a virtual unique number for the node block. So if we change the node block, then we write a new node block somewhere. But the physical location is recorded in the NAT table. So that the other depending node block don't have to update the physical location of the new node block.
So it means the NAT won't be logged when you are updating the NAT. You will log that in.
Yeah. So NAT is updated when we do checkpointing.
Is that in place, right? Or
yeah, in place. Yeah.
That's the in place state.
Yes.
So there is no logging on the NAT.
Yeah, there is no logging. But we have two copies of the NAT. So for the power of recovery. So that happens in a checkpointing scheme.
Okay. By the way, there is another new file system that's called extended path system by Microsoft. So they also claim that this is for the flash devices, especially for the flash devices which is more than 32 GB. And they claim that they have very good performance. So did you have a chance comparing the performance numbers and along with the log? Actually, they provide a transaction and power fill features also.
Which flash system?
Extended file system. It's called FAT64.
Yeah.
So you have the numbers comparison with that at all.
Can I understand your question more clearly?
Okay.
So your question is the ext4 case performance compared to the FTFS?
No. Generally, I have seen more performance with respect to ext5, not ext4. Extended FAT and FAT32 system. Generally, gives a very high performance because of the flash devices are tuned for them. The FAT area region, even though it is in place, right? So it's tuned for the hardware, tuned for those writes are optimized. So is there any comparison with this file system against expat file system? Because Microsoft
we are running out of
any of the document
we can take offline.
It doesn't really matter because expat has patents.
You can't do different numbers, of course. You have nothing to, you can't do an apples to apples comparison. It doesn't work.
So can you have one more question?
So one question is how do you treat the FTL characteristics? Is that guessing, or can you actually read that out of the device?
That's a very difficult point. So, yeah.
So I assume you had access to some of the characteristic specifications which we can't access.
Yeah, we need that kind of information from the manufacturer, actually. So, reverse engineering has a limitation, but even can be done like Arndt Bergman has done a bunch of research for the many kinds of SD card and USB SSD drives. So that's very quite helpful for this case optimization. But eMMC or the very vendor-specific information should be asked directly to the manufacturer.
Yeah, but the problem is then if you have an eMMC card which is replaceable in the phone, how is the user supposed to figure that out? I mean,
If it's eMMC, then it's usually soldered.
what?
If it's eMMC, then it's usually soldered down.
Yeah, but we have the SD card problem, which is basically the same technology, just in a different package. So the user buys those from various places.
But
So
that's very easy to solve. That's in the hardware specification of the SD card that is FAT32.
Or expat in the text.
Yeah, or
XT,
XT.
But if we want to use external SSD drive to be removable, and so we can't use it. We can't use F2FS. We can't find the specification of SSD.
it would be nice to have
Maybe
something.
the zone information is very critical in design, but that's hard to access from the public user point of view. So maybe need some.
The question was more: is there a way to auto-detect things, even if you need to have a table of manufacturers and characteristics for?
I think that kind of zone information or the characteristics are very not confidential in the future, but still manufacturers are keeping that confidential. So maybe this is useful if we try to ask for that information to optimize the whole stack. That's
What is the maximum size of the storage it supports?
Maybe we don't have any limitation of the number of I nodes. So if we have more NAT table size, we can have more I nodes, and yeah, it can be configurable. So just we have only a limitation for the file size because we have only three level indirection like here.
What about longevity? So, I mean, access time is important for flash devices, but so is longevity. So you're showing very good write performance. I'm wondering how that stacks up in terms of usage over the lifetime of the part. Particularly if it's soldered in like an eMMC, we're going to want to see the longest lifespan in the part we can get. So would you recommend this build system as something for a part that's going to be in the field for a very, very long time, or for something that you just want to write to a lot?
Actually, I think the file system access pattern should be very important for the aging condition inside the FTL. So if the file system pattern is very friendly to the FTL, then we could get a very healthy state in the FTL. So yeah, that's the point why we need that kind of optimization from the file system layer.
And you have different algorithms for deciding vectors and deciding your file system. Surely some give longer performance and some give longer lifespan and some give shorter lifespan. So you should be recommending one for performance and one for longevity.
By longevity, do you mean lifetime of that? So yeah, you know, the sequential write is also good for the longevity. So I think this kind of low structure design for the FTL is good for performance and also the lifetime in both aspects. So
Even higher performing write.
yeah,
Okay.
yeah.
Because it should decrease the number of erases. So, I mean, the same thing they're doing to increase write performance is going to decrease the number of erases, which should improve longevity.
Yeah. Sorry, we can take offline questions. So yeah, thank you.